All right, so I just messed up the recording, but we are starting with the MCQ Madness sessions today, which is Summit 22. So we'll be doing all of 2022 as far as we can do them, as far back as we can go. So we'll just be doing the most difficult questions, not the entire papers, just to maximize the effectiveness of these sessions. So we were doing question number 5. The pair of line PQR is a velocity time graph for a car starting from rest. What is the average acceleration of the car over the first 5 seconds? So the average acceleration, if you think about what it means to have an average acceleration would mean the total change in velocity over the total time, right? If it was just acceleration, it would be change in velocity over time, right? Change in velocity over change in time, what we call the rate of change of velocity. But because it's totals, it means the total change in velocity. So from in 5 seconds, it starts out from this velocity, goes here. So that's this. So this vertical height is the change in velocity divided by the change in time. So it's really the gradient of this line PQ, right? The straight line PQ, the gradient of that is the average acceleration. Area below a velocity time graph is displacement, right? So area below the curve or area below the triangle would be displacements. This entire area, this would be basically a displacement assuming, sorry, yeah, this would be the displacement assuming that it went like this. Actually, if it accelerated, if it actually uniformly accelerated from this velocity to here. So this would be the displacement in that case. But as you can see here, this is more than the actual displacement, which would be the area under the curve, right? This would be the change in displacement, right? So it's not this. And the gradient of the tangent at Q would just give us the velocity at the would give us the acceleration at the 5th second, which is not what we want. We want the average acceleration over 5 seconds. All right, let's do 8. When the jet of water hits the wall, it has horizontal velocity V, cross-sectional area A, density of water is rho. Water does not rebound. What is the force exerted on the wall by the water? So here the idea is this, that you can see this water has some velocity V. And because of that velocity, we can also say it has some momentum, right? So let's say there is some mass of water, M, which goes and strikes, and after that, it has no velocity and hence no momentum because it does not rebound from the wall. So if I think about the change in momentum here, in just absolute terms, because final is 0, initial was mv, so it's just going to be mv, right? And then I know to find the force, I must have the change in momentum over change in time. But the problem here is this, that the examiner has not defined m in any way. Because I have density, I know this idea as well, that if I have density times volume, this would become the, what do you call it? This would become the mass. And now I have the cross-sectional area on which it strikes. So for the volume, I can say that it's the area times this length, this water goes through, right? So I can say that the volume is area times length. So if I then talk about the delta P, that would be mass. So instead of mass, I would say rho A L, and there's this V, and it's divided by the time. Now, length over time is nothing except the velocity, right? Length over the time in which it moves is the velocity. So it becomes rho AV and another V. So that just becomes rho AV squared. Some of you might know this expression from heart, which is an especially good thing to do, because then you could have just ticked off the first, you could have just ticked off the correct option at the first site, but otherwise this is how you derive it. Let's actually have a look at the examiner report and let's see what the examiner calls difficult questions in this case. What did we just do? All right, let's have a look at 9 because that's what the examiner report quotes. So a projectile is launched at an angle above horizontal ground, travels through air. Projectile reaches its max height at position X. Assume that no upthrust acts. Which diagram shows the directions of the force or forces acting on the projectile in position X? During the entire projectile motion, the only force which acts on this projectile is the weight X. Hence, there's also only the vertical component of the acceleration. Okay? So in this case, because there's only it travels through air, right? So it travels through air. This is what I missed. Because it travels through air, there would also be air resistance. Otherwise, there would just be weight. Because at this point, it has a horizontal velocity like this. Because that's what takes it forward through the projectile motion, through the rest of the journey. So because it's going to be moving forward, air resistance would be backwards. So air resistance is backwards like this. And there's the weight, which is downwards like this. Hence option B. All right. So I think 10 is also really straightforward. 11 as well, 12 too. Let's have a look at 13. A uniform diving board is held by two fixed rods at points P and Q. A person stands at end R of the uniform diving board as shown. The force is exerted by rods on the board are vertical. The board remains in equilibrium as the person slowly moves towards point Q from end R. Which row describes the changes to the magnitudes of force exerted by the rods on the board? Just by looking at this, you can see that if this person is standing here, he's basically going to, actually, let's talk about this in terms of moments. If this is his weight, you can see that if I look at either about P or either about Q, he's producing a clockwise moment like this, right? Now, if I look at this one, because this rod at this end, it wants to go like this. So this force which would be exerted at P on the rod, it's in this direction. And similarly, if I look here, because this wants to go here, this force which is exerted by this point Q on the rod, this is upwards. The first thing is just to do that, right? So the rod at P and the person's own weight exert downward forces, and the rod at Q exerts an upward force, right? Okay, now let's see this. So the board remains in equilibrium as the person slowly moves from Q, slowly moves towards Q from R. So now the person is moving here, right? Now it might also be very obvious for you to see that this is really this is what I can pretty conveniently take as the pivot, because the board is trying to pivot about Q, right? If I ignore this for a while, right? So this end is going to go up about this point. All right. So as he moves here, you can see that because the distance from the pivot is reducing, so I can see that the clockwise moment reduces. For it to still be in equilibrium, either the anti-clockwise moment must go up, either the anti-clockwise moment must also decrease, or the clockwise moment should increase. So either this or the clockwise moment should increase as well. So then if we see here, this force Q, this would not really be producing any sort of a moment, right? Because this is my pivot. And this force P, this is producing an anti-clockwise moment. So the force at P must reduce so that the anti-clockwise moment reduces. So force at P decreases. But because this is equilibrium, now if I think about the second condition for equilibrium, which is that resultant force must also be zero. So I can say that this force P and this force W should equal Q, right? Upward force equals downward force. So I would say Q equals P plus W. So because P is going down, and W is the same. So for equilibrium, because the right-hand side of this equation is decreasing, the left-hand side should decrease as well. So the force at Q should also decrease. Hence, the answer for this option is A. So a very technical question, this one. Let's go on to another one. Two wires P and Q are made from the same metal and hang vertically from a steel girder. Wire Q has half the length, twice the diameter of P. Identical masses are attached to the bottoms of each wire. Both wires obey Hooke's law as they are stretched by the weight of the masses. What is the ratio of extension of P to the extension of Q? You guys already know how I do this, and in my opinion, it's one of the most convenient methods to do this. The first is you start out from the formula for the Young modulus, which is FL over AX, right? Now, because you need the ratios of the extension, let's make extension the subject. So this would then become X equals FL over AP. Now let's see what is really changing here. So because identical masses are added to each wire, so F is the same, right? And they both are made from the same metal, so Young modulus is also the same. So I can say that X is really proportional to L over A, right? Now, if I think about P, so P, let's say P has some length, P has some area, right? It has some length L, it has some area A. So if I write this down as a fraction, let's say XP over XQ. So let's write it out even more clearly, that this is the length of P, this is the area of P, right? Now, if I think about Q, so it's actually division, let's correct that. So for Q, it has half the length. So here I would say it's 0.5 of the length of P. And the area of P, it's twice the diameter. Now, because area is pi d square by 4, because of the diameter doubling, it would have 4 times the area, right? So this would be 4 AB. Now you can just write this out. Let's write it out as a fraction, LP over AP. And I personally, from childhood, I like to do it like this. It is just reciprocal this. So this becomes 4 AP over 0.5 LP. LPs will cancel out, APs will cancel out. So it's 4 over 0.5, which is 8. So 8 over 1. Let me know if this makes sense. All right, let's go on. It's not really hard. Let's have a look at this one. The graph shows the variation of the displacement of an air particle with time as a sound wave passes through air. Intensity of the sound is halved, frequency remains constant. The graphs below are drawn to the same scale as the graph above, which graph below shows the displacement of the air particle. So if frequency stays constant, then obviously the time period should also be constant, which should be 4 divisions. So in any case where that's being changed, I can immediately strike those out. So if you see here, 1, 2, 3, 4, this is half a time period, so it cannot be this. And similarly here, it's 2 boxes, so it can't be this here. So it's either of C or D. Now, Obviously, whenever in waves you see this word intensity, this equation should come to mind. If intensity halves, there must have been some change in amplitude which was squared, the half of which, the square of which is half, right? So this must then be the root of 1 over d. All right. So here the amplitude was 1, 2, 3, 4 boxes. So it must have changed by this factor. So root half times 4. That's going to give you this new amplitude, right? Because it was 4 boxes initially. So 1, 2, 3, 4. So 4 times the root of half, this turns out to be 2.88. So these number of boxes are what I'm looking for. So approximately 3 boxes. So if you see here, it should be D, right? It's just less than 3 boxes. If you zoom in here, it's not touching the 3 boxes line, slightly less. All right, let's do another one. 28 is what the examiner says. Water waves of wavelength lambda incident normally on an obstacle with a narrow gap. Width of the gap is equal to lambda. Waves from the gap emerge over an angle theta is shown. The gap is slowly widening. Right, so if you look here right now, it's pretty much a lot of diffraction. And you can see that's because this wavelength is approximately equal to this. It then says that the gap is widened, right? So if the gap is widened, what is going to happen to theta? So theta is basically measuring how much diffraction happens and the wavelength. So if the gap is widened, so now it's not equal anymore. So theta, which is the amount of bending really, that's going to decrease, right? And diffraction has no effect on the wavelength of the wave, so that remains the same. Wavelength affects diffraction, but diffraction does not affect wavelength, right? Do make sure that you understand this. Wavelength does affect how much bending would happen, but when diffraction happens, it does not change the wavelength of the incoming wave and the wavelength of the wave that comes out, right? So that's why it's this. All right, let's do 30 here. Also, there's another way that I also recently came across for doing this question. And it's not really a different way, but it's a method in which you can narrow down your options. So this shows light of wavelength incident on a diffraction grating. Separation between adjacent lines is this much. Light that emerges from the grating falls on a semicircular screen as shown from above. Grating is at the center of the semicircle, lines are vertical. How many bright dots are formed? Now, one thing you can remember, and this is again going to decrease the probability of you making mistakes in this case, is that because there is always going to be a central maximum, and then there are going to be some here, and then some here. So this and this, so it's basically 2 times either of these, right? So maybe if it's 2 here, so it's going to be 2 and 2, 4. If it's even 3 here, 3 and 3 is also going to be 6. So this and this, excluding this right now, this would always be an even number. And because we always add this is always going to be an odd number. The total number of bright dots are always going to be odd. So that's why I can strike out these. All right. Now, how many bright dots are formed? Now I know what the answer is either going to be 3 or 7. So even if you were to just work purely on guesswork, now you have you have double the odds of getting the correct answer. But anyway, that's not what we're going to do here. We are going to solve this. So d sine theta equals to n lambda. So n, because sine theta would be 90 for the max number of dots. So d over lambda So D is 2.0 into 10 to the negative 6. Lambda is 5.4 into 10 to the negative 7. Remember, whatever answer you get, you are going to round this down for reasons we have discussed time and again before. 2 into 10 to the negative 6, 5.4 into 10 to the negative 7. Turns out to be 3.7. Rounding down, this makes it 3. So 3 on each side. So 1, 2, 3, 1, 2, 3, and the one in the middle. So 2 times 3 plus 1 is 7. All right, so do make sure that whenever you have a question on the number of bright fringes or bright dots on the screen in a diffraction gradient context, it can only ever be an odd number. It's never going to be an even number. All right, what else do we have here? '33 is seemingly tricky. All right, so 33 says the current shows the IV characteristic for a semiconductor diode, which statement can be deduced from the graph. Above a certain positive potential difference, the diode obeys Ohm's law. Now, it does appear here that if I go beyond this point, the line becomes straight, right? Is this a reason for it obeying Ohm's law? And if you have done some paper 2 questions related to diodes, you will find that this is not the case. If the gradient is constant, which it is in this case, it does not guarantee a, what do you call it? It does not guarantee that it's Ohm's law, right? Remember that resistance is just the ratio. It's not the gradient. All right. So it could be the case, it could not be the case. But if we look at all the options together, we find that there is a more sensible option than this. I'm just saying why A is not correct, right? So also you can think about it in this way, that Ohm's law basically says V and I are directly proportional. For directly proportional lines, if I'm thinking about a graph, just a straight line does not suffice, right? Any straight line does not suffice. Instead, I need a straight line which goes through the origin. So you can also see that if I extrapolate this, it is definitely not going through the origin. So this is wrong. Current is directly proportional to potential difference when the current in the diode is in one direction. Again, it's not directly proportional. Otherwise, it should have been a straight line. Diode has zero resistance when the current in the diode is in one direction. Again, it's definitely a small value, but it's not zero, right? There is some V, there would be some I, the division of which would also give some non-zero value. And the resistance of the diode depends on the potential difference. This is absolutely correct. It does depend on the potential difference, as you can see. When V changes, I also changes accordingly. So resistance would also change. 34, a resistance, a wire has a resistance of 30 ohms. Second wire is made from the same material. So this means resistivity is the same. Same mass, mass has no effect on resistance, and is 3 times as long as the first wire. What is the resistance of the second wire? All right. Oh, so this actually does have something to do. Now let's look. Same material means resistivity is the same. And it would also mean that every other material property is the same. Remember that we use the symbol rho for density as well as resistivity. It has the same mass. So if I think about this, rho equals to m over v. If density is the same, mass is the same, this also means the volume has to be the same. All right. So if it's 3 times as long as the second wire, as the first wire, so if I think about volume as cross-sectional area times length. So if it's 3 times as long, it would only have 1/3 of the cross-sectional area. Because of volume being constant, area and length are basically in inverse proportion. So what is the resistance of the second wire? Then if I think about this relationship that R is proportional to length over area. So tripling of the length would also cause tripling of the resistance, and having the area become 1/3 of what it was would also cause it to triple because of the inverse proportion. So this is 30 times 9, which is 270 oops. All right. So this initially, I also felt that this is some irrelevant information, but it was actually pretty relevant because you had to think that the volume is also not going to change here. Good question. Yeah, so that's it for this paper. If you guys have done this and if you want me to do any other question, let me know. Otherwise, we'll go on to the next one. Other questions are somewhat easier. That's why they haven't been mentioned in the examiner report. All right, just go through this. We were doing summer 22 paper 1-1. If you have any questions, let me know. All right, let's move on to the next paper. This one is summer 22 paper 1-2. The examiner says question number 4 was somewhat tricky to students. Really shouldn't be because it's just vectors. So an object is moving with initial velocity as shown, final velocity as shown. We need to find the vector which represents the change in velocity. So change is v minus u, right? But this is u, so minus u would be the same vector but pointing in the opposite direction. So this is your minus u, right? So just according to the head to tail rule, if you put it together, so the v minus u arrow, that would be pointing like this. This is the resultant, so it must be v. Let's have a look at 5. Car travels anti-clockwise along a horizontal circular road of radius 12 meters as shown. The car takes a time of 4 seconds to move from position P to Q. What is the magnitude of the velocity of the car from the journey P to Q? Right? So it's going from P to Q in this direction. But it's the velocity. And hence, because it's the velocity, this is the displacement over time, right? Total displacement over total time, because this is average velocity. So total displacement, if it goes like this, or if it went like this, it's just the straight line distance between the starting and ending positions. So this length is what we need to find. All right. So this is 12 because this is also a radius. This would also be 12. So this is just a right angle triangle of which we need to find the hypotenuse. So 12 square plus 12 square under the root. So this would turn out to be 12 root 2. And how much time does it take? It takes 4 seconds, right? So this would be 3 root 2, which would make it 4.24. So A is the correct option. If the examiner was asking you for the average speed, then it would not be this distance because it has traveled this entire distance. You would have to calculate all of this. which would basically be 3/4 of the circumference, right? So you would do 3/4 of 2 pi r. That would be the distance, and time would be the same as 4 seconds. But because this is velocity, it's displacement. The next one is 8. Again, a really tricky question. If you don't know how to deal with connected particles, some of you might recall this from doing this with me in class. A child of mass 20 kg stands on the rough surface of a sledge of mass 40 kg. The sledge can slide on a horizontal frictionless surface. So the sledge, the surface of that is rough. So the surface of the sledge itself is rough, but this surface is frictionless, right? So there is some friction here. The rope is horizontal. The child pulls on the rope with a horizontal force of 12 Newton. This causes the child and the sledge to move with equal acceleration towards the pole. So both of these move towards the pole. What is the frictional force between the child and the sledge? Let's start out by marking the different forces on these two things which are here, which is the child and the sledge. So if the child is pulling on the sledge, there's going to be definitely some tension in the rope. Because I'm talking about the child right now, this tension is going to be marked away from the child. And there is going to be some frictional force which should be in this direction, right? So there is tension and there's force. And everything is accelerating in this direction towards the slope, towards the pole. And then we know this horizontal force of 12, and we'll work with that in a minute. And you have a force here of just equal to the T, which is pulling this sledge towards the pole, right? So now what we do is we write out Newton's equations, Newton's second law for both of these. First, we do it for the child. So we would say T minus F equals to ma, m being the mass of the child. If I want to write it in terms of the things that we have, so tension is 12, F is what we want to find out, and the mass of the child is 20, and this is 8. If I do the same thing for the sledge, this would just be T because there is no other force on the sledge. It's frictionless. So there's just this T being equal to, what do you call it? Just the T being equal to ma. So T, which is this 12, equals 48, right? So I can see here that because 12 equals 40a, in the first equation, I can substitute this 40a minus f equals to, just so because these are two simultaneous equations, you can make any one thing that you want subject of this equation. Actually, just from this one, 12 equals to 40a, you can get the acceleration, right? So acceleration is 40 over 12, and then you substitute that back into this equation. So 12 minus f equals 20 times 12 over 40, which is going to be 1, 2, 6. So 12 minus f just a second. I think I may have made a mistake. The setup of these equations. Oh, yes. How can I forget? Apologies. First equation was fine. But because of Newton's third law, this friction, which is basically the force which the sledge exerts on the child, because of that, there's also going to be a Newton's third law there, which is going to be the friction that the child exerts on the sledge. And hence, this is going to count as a force which the child exerts on the sledge then, right? So this should then be in our equation here. So then it's going to be T plus F, so 12 plus F equals to 48. Now, when I work with these, if I add both of these equations together, these cancel out. So this becomes 24 equals to 60A. And then you can calculate A and plug that back into either of the equations to get the F, right? So 12 minus F equals to 20A. So F would be equal to 12 minus 20A. So 12 minus 20 times this thing, which is 4 meters. Again, this, in my opinion, is one of the most difficult questions I have ever seen on dynamics. So make sure you get this one. All right. After this, we have the next really difficult question is 20. A wire is being stretched by a tensile force. Which statement about the elastic limit must be correct? The deformation is plastic after the elastic limit has been reached. Just a second. So yeah, A is definitely correct because that's just how the elastic limit is defined, which is that it's elastic deformation up to that point after which it is plastic. This one says the deformation is plastic until the elastic limit is reached. This is outright wrong, right? The deformation is elastic until the elastic limit is reached. C, the extension is proportional to the tensile force after the elastic limit has been reached. So extension proportional to force. So this is talking about the limit of proportionality, really. So if I just make a small graph here. So the graph looks like this, and then it goes like this, and then you have something else here. So in this case, if we look at this, again, let me redraw this. So it's a straight line, and then it curves, and then it curves again. So this is probably the limit of proportionality, and then you have the elastic limit. So it says the extension is proportional to tensile force after the elastic limit has been reached. So after the elastic limit, we don't have proportionality really. So that's why this one is wrong, right? And if we look at D, extension is proportional to tensile force until the elastic limit is reached. So usually the idea is this, and I have talked about this in the lectures, that limit of proportionality and elastic limit is usually very close together. And they may also, in some cases, be the exact same point. But a wire can also be elastic after this, right? So it's not like it's just proportional up until the elastic limit. It can also be proportional after this one. So that's why D is wrong. The only correct one here is A, which is always universally true. 22. So a transverse water wave is moving along the surface of some water. This causes the ball to move vertically without moving horizontally as it floats. At one instant, the ball is at the position shown. The wave has a frequency of this much, amplitude of this much, distance between a trough and an adjacent peak. So you can see this is half the wavelength is 2.4. So the actual lambda would be double of this, which would be 4.8. What is the distance traveled by the ball in a time of 20 seconds? So first, if we figure out in a time of 20 seconds, we have the frequency, right? So from the frequency, if we find out the time period. So a time period is going to be 1 over 0.2, which is going to be 5 seconds. So this really corresponds to 4 time periods. Now this ball is not going to move horizontally. This is explicitly stated because this is a transverse wave. Let's think about during one time period, what distance does the ball move? So if this is where it is at time t equals to 0, it would go down, then up, and then up. So in one time period, it covers 4 amplitudes. Hence, in 4 time periods, it would cover 16 amplitudes. And the amplitude here is given as 0.7. So 16 times 0.7 is 11.2 meters. All right, so the ball does not move horizontally. This is a transverse wave, just moves up and down. All right, 23. A sound wave travels from left to right across a room. The variation with distance across the room of the displacement of air molecules at one instant is shown. At which distance will air pressure be the lowest? So, air pressure being the lowest, how do you select this? So you have a displacement distance graph. All right. So if you look at this one here, air pressure being the lowest basically means that the examiner is talking about a rare fraction, right? Because for the air pressure to be lowest, the air molecules are most widely spaced. All right. Okay. So now for this case, you can see that as we go from C to D, all right, so you have A, which is a point of max displacement, C is a point of minimum displacement, and B and D are zero displacements, right? So this is basically either going to be a rare fraction or a compression. So what we can do here, and this is a technique also that I have taught you, which is if you draw 5 points like these under the graph. So let's say you draw 1, 2, 3, 4, 5, right? Now, as the sound wave is going to pass, what is going to happen to all of these particles, all of these points basically? Because right now these are at the equilibrium position. So if I look here, O is not going to move, A is going to move to the right, B is not going to move, C is going to move to the left, and D is going to be at its original position. So look here, O is not moving, A is moving to the right, B is not moving, C is moving to the left, and D is not moving at all. Which particle is the most isolated from the others? That's D. All right, that's how you do questions like this. '26 we've done time and again in class. Let's have a look at 28. So for some reason, people do make mistakes with this question related to diffraction and gap widths. So the waves pass through a gap of width x so that diffraction occurs. Which combination of vibration frequency and gap width will produce the smallest angle of diffraction? So least diffraction means that you need to have the most difference between the wavelength and the gap width. So if you halve the gap width and if you halve the frequency, this would double the wavelength, right? So twice of the wavelength and halving the gap width, this does increase the distance between the two. Now, if we think about B, so B does halving the frequency, which means doubling the wavelength and doubling the gap width. So this doesn't have as much of an impact because both of these are increasing. C, so C is when you have a halved wavelength, halved gap width, right? So this also does not have any major effect because it's still pretty much equal. And then there's D, which is doubling the frequency, so halving the wavelength and doubling the gap width. All right. So now, which one do we select out of A or D? And the answer is this, that if you have the smallest wavelength versus the largest gap width, that is going to lead to less diffraction as compared to this. If you have a small gap width, there would still be some diffraction. Yes, it would be reduced, but there would still be some. But if you have a very, very large gap width, this is going to lead to almost no diffraction whatsoever. That's why D is the answer. So do remember that as opposed to a gap width being very small, or as opposed to gap width being very large. A very large gap width reduces diffraction more than a very small gap. So the last question we are doing for today is this one. A potentiometer circuit is used to determine EMF of a cell. The circuit includes a second cell of known EMF E0 and negligible internal resistance, uniform resistance via PQ. EX is less than E0, right? This is a requirement of this method to figure out the EMF of a cell. The movable connection can be positioned anywhere along the length of the resistance wire. Which circuit is suitable for determining EX? So if you look here, so there are some differences that you can see in all of these. So first off, you can see that there's some difference as to how E0 and EX are placed, right? That's a difference. Where the galvanometer is placed is a difference. And the polarities in which these are matching up, that's also a difference. So if I look at A is wrong because the polarities should be the same poles, the same ends of the cell should be connected together. So this is really forming another more powerful cell, which is not what we need. We need the same polarities connected together, so it should be plus plus, minus minus. That's why this is up. B is connected minus minus. B is also connected plus plus. The galvanometer is also connected along the movable circuit. But the problem here is this, that since EX is less than E0, EX should be along with the movable contact. It should be EX, right? Because a fraction of E0 would be appearing here and EX should equal that. If what we are doing is this right now, because EX is less than E0, then whatever fraction we take of EX, it's obviously also going to be less than E0. So that's why this is out. C, so you do have it connected correctly. E0 is like a part of the major circuit, EX is with the movable contact, but the galvanometer is connected the wrong place around. This galvanometer will never read 0. It will always have some reading because of current flowing into this path. So this is wrong. And because of all the shortcomings in the other ones, D is actually correct. EX is connected along with the movable contact. Galvanometer is also with it, and it's also negative, negative, positive, positive. So this is D. All right, so that's this paper. Now, in the next session, we'll be going through the rest of the papers, and we'll be trying to do as much of them as we can. All right. Thanks for your time, guys, and see you tomorrow. Bye.